Hello Commanders, Commander Placer here, and welcome to today's Zencast. And as usual, I am joined by Proxim.
Hey, what's up guys? How's it going?
And today we have a special guest with us, which is Down to Earth Astronomy.
Hello.
And today we're going to be given a bit of a science lesson, and hopefully we'll learn something new. You guys will learn something new. I'm pretty sure I will already. I don't know about you, Proxim.
Probably. I expect to be schooled and feel like a complete moron by the time this is over.
I would consider that a win, I think. Like, learning is good. So, currently, as you guys can see, we are sat just above the rings of Saturn. We've got a couple of topics that Astro wants to talk us through, and we're gonna, I guess, get to it, I suppose, because there's going to be a lot of science, isn't there?
Yeah, there should be. But we should actually probably try to get a bit closer. It could be fun to try and get into the actual rings. Or maybe we should actually start by just looking at... if we start by just looking at the rings, one of the most notable things that I think is quite interesting, but something they modeled pretty well in the game actually, is you will often see rings have a different density at different distances. And these distances are actually caused by the moons around the planet. So you can actually use the colors of the rings to determine where the moons are around the planet. Because imagine if you had a completely smooth ring where every rock would just be completely evenly distributed in the ring, and it would have the same color through the whole ring. And you then put a moon. The moon will then try to pull the rocks into an orbit where when the moon orbits the planet once, the rocks will orbit the moon twice. So they kind of go into a harmonic with each other, and that's why you get these different colors at different distances around the planets.
So the science has started.
Yes, it does.
Oh God, this is going to go so. This is going to go so over my head.
Science is good.
Yeah, don't get me wrong. I love science. Otherwise, we wouldn't have science fiction games. But man, this is going to be above me. But okay, cool. So different densities.
I'll try to keep it at a level where everybody can keep up. And if I end up going out on a tangent somewhere, just stop me, because I'll do that if people ask me to talk about astronomy.
Hey, Great Test just got it. He says science is good for you. It is.
Yeah. Agreed.
Matt the fat guy says, explain like I'm 5.
Yeah, I think that's probably going to help me as well, because that's kind of that's the level I got to with space. So, so are we heading into the rings?
Yep, let's do that.
Sure, why not?
I'll just follow Placer in or something. Great test is actually a bit, currently a bit low. I can also move the microphone a bit closer if that's a problem.
Cool. I will have a little tweak.
Ooh, you know what? I have never tried this with Saturn's rings before. There's a gap between like this really thin outer band and like the thicker parts of the ring. I wonder if I can fly through here.
The Maxwell gap?
Yeah.
Or
nope. It'll drop you out. God dang it. That's disappointing.
Well, the gap in between rings even, sorry.
Wingdings?
Wingdings. My favourite font. No. But yeah, so the gap in between rings, you mean where you can sometimes dip in them?
Yeah, sometimes you can dip through and like weave in and out of them.
I think you can only, in game terms, you can only do that if the rings are designated in the games as different rings, but the rings of Saturn is actually counts as one ring in the game, so they're basically one rigid structure.
Well, I will say there's not very many asteroids here, very few.
Well, there shouldn't be.
Oh, have you dropped down already?
Oh, in my spot, yeah, I crashed right into it. It dropped me out.
Oh, okay.
It's like no super cruise for you.
Oh, this is bad. I'm kind of like in the gap, so yeah, I see what you mean about the gap and stuff. So yeah, so Matt's asking what determines which materials and minerals are in asteroid belts / planetary rings. It's a good question.
I guess that depends. That depends on the initial cloud that the system was formed from. You will notice if you're in a system that in the game all the rings have these different rarities like pristine or high density. I can't remember the old. I mean, I only look at pristine rings when you're out mining, the one that give the best materials. But if you found a system with a pristine ring, you know that all the rings in the system are pristine reserves. And that's basically because the rings are formed from the same planetary nebula or planetary cloud when they was originally formed. And what determines what type of material is the distance from, would often be the distance from the main star. So in general term, as with anything, there are exceptions. But generally, you should see that metallic rings and rocky rings would generally be around planets close to the main star, and icy rings would be further out. There we go.
Now, we just had a question from Alex in chat, or Fat Waffles, about Saturn's rings being very thin.
Yes, they are very thin. In reality, they should be averaging about 10 meters thick. And if you compare that to, I think, yeah, we have Peroxide and Anaconda. The Anaconda is 150 meters, 152 meters long actually. So the Anaconda should be able to fit something like 15 times, or should be the ring should only be a 15th of the length of the Anaconda, and clearly they're not. And I guess that comes down to gameplay reasons, because in reality, what you would often see when you go into a ring, most of the asteroids out here would be around the size of the particles that you see in cigarette smoke. That's the size the rocks should be, but that would make them very hard to target and mine. So I guess that's why they decide to make the rocks quite a bit bigger. I mean, there are some places where the rings are up to 10 kilometers thick. So they do exist in this thickness as we see them here. I don't know how thick they are, but I would probably guess that these rings here are about 10 kilometers, maybe a little bit less. But in general, they are way too thick compared to what they should be, and the rocks are also way too big. There are rocks that are several meters in radius in Saturn's rings, but the biggest rocks should be about the size of a school bus. I think we can very easily agree that just the rock that's just actually right in front of the plate right now is way bigger than that.
Yeah, definitely. It definitely will be, yeah. Because I'm not sure how big a Diamondback Explorer is, but I'm thinking it's about the same size as a bus, quite easily. Like,
yeah,
probably much bigger than that, in fact. So there are a few guys in the chat who are saying they get buffering and stuff. I don't know if any of you guys are, if you two are watching at all at the same time.
I am.
Any buffering problems?
It looks fine to me.
Okay. That could just be YouTube playing funny then. But yeah, because I'm obviously watching a lot at the same time.
Sometimes. No,
it looks to be okay.
Fine on my end. I have no problem trying to refresh to see if I get any issues, but try to rebuffer the stream. Nope, works fine.
Okay, good. Just thought I'd make sure.
At least on my end. It might be if people are overseas, I don't know.
Now, here's a question. It's going to sound like a totally daft question, but what causes planets to have planetary rings? Like, well, what makes that happen?
So then we need to go all the way back to how planet systems are actually formed to start. It's actually a good question, because we don't really know. But if we look at everything else that has rings, we can kind of get a guesstimate of how these things happen. So basically, when a system is formed, like a solar system is formed, you have this cloud of gas, and that initial chemical the chemical components in that gas, or how polluted it is, as we say in astrophysics. In astrophysics, everything that's not hydrogen and helium is counts as pollution.
Okay.
Or metals, just because everything that's not a gas is apparently a metal. It's easier that way. But anyway, so you have this initial cloud, and that will often be disturbed somehow. It might be that a galaxy arm is going through the gas cloud and disturbing it, or it might be a local supernova going off. Something, it might just be another star actually forming, disturbing the balance in the gas cloud. And as you can probably imagine, if you've just been outside looking at clouds, if people ever go through that, you will have a feeling that there are places in the clouds that are more dense than others. They're not completely uniform. And those places that are more dense, the same thing happens in planetary nebulas. And then the gas will just begin to collapse towards that point, the more dense points, because there are more mass there. So of course there's a higher gravity at that point. And it will then begin to collapse, and the cloud will then often also be spinning along some axis. There could be some weird axis, but they will be spinning, and that will cause the gas cloud to go from a approximately sphere into more like a spinning disk, and gas will then begin to fall first downwards onto the disk and then move inwards towards the center, which formed the main star. And after like 99% of the mass has collapsed into the main star, you have all the leftovers left, which is what forms all the planets. And then now you have pretty much the same thing happening, just on a smaller scale. So you now have a disk, and inside this disk around the star of gas and dust and small particles of everything, and they slowly begin to collide with each other and form larger and larger clumps of gas or rock, until they are large enough that we call them planets. And then pretty much the same thing happens, that each clump that begins to collapse in on itself will, of course, begin to spin as it falls in, just like if you've seen a figure skater, if they have their arms stretched out, they will spin slowly, but if they pull their arms in, they'll begin to spin faster. Same thing here. So even though the initial cloud is spinning very, very slowly, it might be almost unnoticeable. As it collapses, that small rotation will be amplified and begin to spin a lot faster, which will then, of course, form the rings. So it's expected that most planets actually has rings right after they're formed. Sometimes it will just fall onto the planet and be part of the planet, or in other cases it will begin to collapse and become a moon. So that's how planet rings. And in cases like this, some of the moons, there were so many moons formed that some of these rocks will never actually collapse in on just become a proper moon. They will just be sitting there.
Okay.
What's going on, guys?
That's the short answer.
Gotcha. Oh, Minnie, you having a gate crash?
Oh, what now?
We're in the middle of a we're in the middle of a Zencast, Minnie. You're gate crashing.
Oh no! I'm not even watching it. I'm at work.
Well, you should go and watch it. We're doing science today.
All right, I'll go check out the stream soon.
Thanks for dropping in, though.
I had a new terrible idea for another video. I'll fill you guys in after the cast.
Okay, man. We'll catch you later.
Laters.
That is classic Minnie. He's seen us chatting and he's like, I've got to get in on that. God. Right. So, I kind of want to know what he's doing now, but we've got science to do. So we've been over the planetary rings and how they form ish, because we're not 100% sure it's that kind of thing. And okay.
And now that we actually are talking about planets and planetary or solar system creation, have you ever noticed when you're flying around that all the rocky worlds are often close to the star, and the gas giants are often further away?
Yes.
I would imagine that's because the stars, like they just kind of pull all that material to them.
It's actually quite the opposite. They push the gas giants away.
Really?
What? No, wait, hang on. This goes against all logic for how everyone assumes things work. Well, me anyway.
So we have to go back to that point where we have a pre-main sequence star. That means that before the star is a star, it's basically a protostar. So you have the fusion process has started and in the middle, but the planet's not yet formed. So we're still that whole everything's collapsing onto a disk and falling onto the star. But the star has reached a point where it's actually ignited, and the fusion process has started. But the planets will not have formed yet. It's still just a disk of gas. And I think it was actually you, Broxus, who posted an image I saw on the ZENcast, where you had this 2 Centauri stars, and these lots of smaller Centauri stars as well. That's basically the way that the Stellar Forge, the program that Frontier is using to generate all these systems, that it's simulating that all these Centauri stars that you see are basically just trying to emulate the ring of gas that's around the newly formed star. But as the star ignites, you will have, of course, you will have gravity pulling everything in, but you will also have radiation pressure from the sunlight. So that's how solar sails work, for instance. We'll have the sunlight actually pushes on you. It's a bit weird to think about, but sunlight actually has an impulse, so it can actually push on things and apply kinetic force to objects. Very, very small though, but it exists. But it's enough that in this early stage where the planets are not yet formed, all the lighter materials, they will be more prone to be pushed away by the main star. So all the light elements like gas will be pushed out to the outer part of the solar system, but the heavier elements will be able to remain close to the star because they are more dense. So it requires a larger pressure, radiation pressure, to push them out. So the star would have to be brighter in order to push them out. That's why you end up having a disk where all the heavy elements will be collecting close to the center, and the lighter elements will be gathering out further out. So that's why you get the gas giants at the outer edges of the solar system, and all the rock or solid planets closer to the star.
Okay. I guess that makes sense. Proxim, does that make sense to you?
Yeah, I get the idea. I feel like I'm back in like elementary school for astronomy again.
What I'm gonna sorry, I was gonna say because I think people are having problems with buffering. I'm still hooked up to the backup ingestion server, so I'm just going to quickly restart the stream on the normal server, the primary one, and hopefully that should make a difference. So guys, go nowhere. I'll be back in like we will be back in 5 seconds, and it won't take long at all. We're restarting, so hopefully that should be back up and running in no time at all.
Hopefully.
It just came online on my end, at least. Oh,
yeah.
Now it's buffering.
Classic.
Let's see.
Okay, so we should be back, guys. Let me know if that is better. That hopefully should be. And
oh, there we go.
We'll
refresh worked.
So that is classic Mini.
Yeah. Oh man.
Okay, so I think what we might as well do, what it was during game, is head over to Jupiter.
Yeah, let's do that.
Because I already had no clue about the fact that it had rings until probably only a couple of years ago, which I don't know whose fault that is, but I'm pretty sure it's not mine.
That is your fault. There's no getting out of that one.
How far away is Jupiter?
5,192 light seconds.
It's nothing. It's just around the corner.
Well, considering that I flew like 3.5 million light seconds to give some guy fuel earlier. this is nothing.
Oh, we could probably do that at Jupiter as well.
So at some point I will need to do the hut and run. That's...
Oh, great test. Yes. Yeah, that happened to me a whole bunch of times on stream the other day. I ended up having to switch my on-screen stream chat to Streamlabs thing. YouTube has been very finicky lately.
I hope it's because they're improving it.
I think they broke it.
No, I'm going to go with they're improving it. Let's be super positive about this.
Okay, all this stuff started happening the same day that they changed the subscribe button and all that nonsense, so they broke something. I'm almost positive of it. Let's not let them off the hook, dang it.
So, bizarre question from Daniel in there. What if we're in a simulation like the Matrix?
Then there's going to be one hell of a computer running small computers inside it.
Yeah.
No kidding.
Simulations of the simulation that computer is running. Okay, yeah. Anyway.
Mini. And Yamix, welcome to the stream, bud. Hope you're doing okay. We're learning. We're trying to learn about stuff.
I feel a little special right now.
What, as in like that kind of derp? I science.
A little bit.
I can has science.
Yeah, pretty much.
But now that we're actually talking about planet forming, for a very long time, the theory that we just discussed has been pretty much the accepted theory, and what people would believe was how planets were formed. And that was until we began actually discovering exoplanets, so planets outside our solar system. Because the first couple of hundred exoplanets that we found were all gas giants at the size of Jupiter or larger, orbiting this closer to the star than Mercury, basically. And then people begin to think, well, hold on a second, is the solar system just an oddball? Is there something weird going on here? Is this why there's life in this specific system? But what took some time before people realized was there's of course a huge bias, because the way people were discovering the first exoplanets were that they were looking at nearby stars, and they would look at the star wobble from the other planets pulling in it. And of course that star wobble is a lot more noticeable when you have a huge planet like a planet the size of Jupiter orbiting very close to it.
That makes sense. Now, yeah. I watched something about how we can tell what the atmosphere of a planet is based on the wavelengths of light that can pass through the atmosphere. Is that right?
Yeah.
Oh, good. I know science.
I actually did when was that? A couple of months back. I did a small simulation of it for a video I did. And so one of the methods that we use today to discover exoplanets is we're basically making a telescope just stare at a star for an extended period of time. Or it can stare at several stars at the same time, because that's apparently how telescopes work. But what it will do is it would look at the star and it will measure the brightness of the star very, very accurately. And then it's going to wait for a dip in that the intensity, and then after some time it will go up again. And that's when a planet is moving in front of the star. So the planet is blocking some of the light from the star, which causes a dip in the total intensity of the light from the star. But of course, if that planet then has an atmosphere, some of the light from that star will pass through the atmosphere. So by looking at how the spectrum of the star is when there's no planet, and then looking at how the spectrum is when there is a planet, and then subtracting the two, you kind of get what's the difference in wavelengths, not just intensity, but what's the difference in wavelengths. And then the additional stuff that's there, or the stuff that's been removed, can then tell you something about what type of elements are in the atmosphere of the planet that moved in front of the star. It's very faint, but you can do it.
That's something I always found like amazing when they say, oh, you know, you can oh yeah, we know what atmospheres are, especially before we had probes get there, you know, like what atmospheres are on even the moon's other planets in Sol. It's kind of a how, and then, you know, knowing that you could just look at something and be like, oh, that's this, is an interesting thought. Like, in the grand scheme of things, you know, how did someone come up with that as an idea?
Well, that's a problem with astrophysics compared to many other types of natural science. I mean, if you look at, let's say, biology, for instance, you can always try to, I mean, you have your sample right there in front of you, and you would often have the ability to take that sample or maybe alter it slightly and see, oh, what happens if I make some generic modifications to this? How does it then react? What happens? You can't really do that to to the soul or to the universe when you're observing it. You pretty much have one universe, you can't change it, you're just stuck in one place looking at it. So the only way we can actively change what we're looking at is by simulating it in big computers. Which is of course massively expensive, but it's the only choice we have.
Yeah, I suppose there is that. We don't know what happened before, we only know what's happening now, and we can predict what's going to happen in the future and observe it as it happens. But obviously it's all happening very, very slowly as far as we're concerned.
Yeah, exactly. You would have to wait for quite a while if you want to see the actual evolution of the universe, because, well, within our lifetime, it's basically nothing in the grand scheme of things. So we're basically stuck at sitting in one place. We have a snapshot at the universe, and now we're trying to figure out what happened 3.5 billion years ago, which can be quite difficult. But that's where large computer simulations come in handy, because you can basically just put in your, if you can emulate your theory, like, I expect the universe to be developing like this, and you take all that physics and all that math that you have and you plug it into some huge computer somewhere, and then you say, okay, what happens if the initial conditions for the universe are like this? And then you ask the computer to just begin to evolve that in time, and then you wait for a couple of months, and then you get a result, and then you take that result and then you compare it to the observations that you actually make about the real universe and say, is this vaguely similar? If no, well, go back, find some other initial conditions and try again.
Months at a time.
Or alter your theory. Yes, that's a lot of time.
Well then. Okay.
There's a lot of programming and code optimization when you do astrophysics. There are very few astrophysicists today that actually looks in telescopes, and they actually today we actually distinguish them as two different type of science. We have the astronomy and we have astrophysics. Astronomy is looking into a telescope, and astrophysics is, well, either making pen and paper predictions or simulating stuff in a computer. Often in broad terms.
Okay, because to me it's all kind of similar, because it's kind of very much that if I don't get it, I don't understand. It must be magic almost to a certain point, which is I mean, I'm more of a biology and psychology person. Turgeon, got a question. Stellar Forge just loves making planets with tens of millions of Earth's atmospheric pressure and surface temperatures hotter than the boiling point of tungsten. Is that a question?
I guess you ask if that's realistic. So that's a difficult question to answer because as of right now, we have discovered, I think we are a couple of thousand exoplanets, and many of them we don't know anything about their atmosphere or mineral composition. We just know that they are there. Maybe we have a vague idea about the size or and how far they are from the star, but there are very few of them that we actually know in detail what their atmosphere is like, if they have one, and surface pressure, definitely, that's also a very difficult thing to measure at large distances. So it's hard to predict whether that is accurate or not. It could go either way.
Okay.
Just a quick note: if you guys want to see something cool, drop down to where I'm at.
Okay.
Yeah.
This is the literal edge of this ring. I am at the corner where the asteroids stop, and then there's empty space between here and the planet.
Oh, cool. I've always wanted to do that. Oh. Going too fast. Going too fast. There we go. Oh, that's pretty cool.
I've never actually tried this before, so...
This could potentially be a very awesome sight.
It is. It's pretty weird. I kind of get the feeling that I'm not supposed to go in there.
Oh. What?
Yeah, I found if you do it right, you can zero in on the very edge of the asteroid belt, the ring, and it'll drop you right on the edge of it. Kind of cool.
This is like...
Are these guys clean? Yeah, they are. Because I have no weapons, and Plato has no shields.
I've got no weapons. I've got no shields.
I have both.
Well, that's good. I don't have particularly good piloting skills either, so it should be an interesting...
And qualified ESA engineer says our data might be incorrect. That's true.
Yeah, I suppose that's the thing as well, is that we could actually be wrong about everything.
Entirely possible.
I guess we have... I mean, some of it must be right, yes, but some of it is probably wrong as well.
But yeah, so in game, I have come across a Hasros that was actually in between the gap between what I thought was two rings, but turns out it was a very, very, very sparse ring. And then on the outside of it, a denser one, and on the inside a denser one. Now, would that happen in real life? But bring it back to the rings because they fascinate me. I think that's some of the coolest things.
If the moons around the planet have are at the right distance and have the right mass, sure thing, why not? I mean, if you just look at the rings of Saturn, you will be able to find spots like this where you would have a high gradient in the density.
Okay. It's always good to know that what you've seen is reasonably realistic.
As long as you don't drop out and go into the rings, then yes.
Cool. Shall we go on to the next place on our journey?
Yeah.
So we're
that again?
I have to double check. I said we're going to
LSH something.
Lalande 25224. I can't really remember what's in there though. Why did we choose this one?
Can you post that somewhere?
We'll find out when we get there. It'll be a surprise. It's a mystery tour.
Can you post the system?
Yes.
Lalande?
I've bunged it in the chat, so if anyone wants to know what we're off to look at, you can go and have a look.
That works for me, because I'll never figure out how to spell these stupid system names otherwise.
They are also in the Zencast chat as well, from yesterday.
Alright. Off we go.
Yep.
I'm still stuck in Matchlock.
I'm doing the very same thing that I spent ages upon ages doing over the last week and a half.
What, jumping?
Yep. Lots of
there.
jumping. I have 5, then. I kind of weighed this thing down a little bit.
What's your jump range?
Now?
Yeah.
35.35.
Okay. Astro, yours?
57.
Oh, wow. That's pretty good going.
Yeah. The bubble boss for the win.
Well, aren't, you know, going back to rings for just a second, because there's some comments there. Aren't Saturn's rings fairly young?
That depends. I mean, define fairly young. on what scale? I'm actually not 100% sure when Saturn's rings were formed. But I would expect that they have been there for quite some time. We should probably have looked at it. We'll do that if we find another ring planet with moons around it. If you go to a planet with rings and you go to the first moon that the planet has, there's a very high chance that that planet will have these deep canyons on it. That should be pretty common. And that's because Minnie keeps posting stuff.
Yeah. That's Minnie all over the place.
He keeps super chatting and saying things. This is actually really funny.
The thing is, you can't be too mad about it, can you? So,
No.
so, Minnie, acknowledged, I will think about it. There you go. I could do an Iron Man, I suppose, is that.
Don't do it in open.
Well, then it would be Iron Man, would it?
Yeah, sure it would.
But right, so, what were we talking about? Ages of rings, right? That was the...
Yeah.
Okay.
Yeah, we're talking about the canyons on moons close to gas giants, or to large gas planets. As you can probably imagine, the closer you are to a planet, the stronger the gravitational pull is. So, as a moon orbits around a gas giant, the pull on the side facing the planet is larger than the pull on the side facing away from the planet, the gravitational pull. And that pull, of course, moves around the planet as it orbits, unless it's tidal locked and always have the same side facing towards the planet. But if it's not tidal locked and it actually rotates, and that pull will then move around the planet, and that actually causes the outer layer of the planet to break up into pieces, and along those lines you get these deep craters. Or not craters, but canyons. So it's basically the moon being pulled apart.
Got it. And that's similar to, that's the action that takes place on one of Jupiter's moons, isn't it? That keeps it, because it doesn't make any sense why it's as warm as it is, so it has to be geothermal energy that's keeping like they're being liquid. I think
This is why we went here.
Yeah, we did. this neutron star. Yeah, that was it. That was the one. Quite a nice neutron star. And I did say that we were going to try and get boosts off of this one as well when we go.
Oh, I'm gonna fail at this. Horrible neutron star boosting.
I wish you'd have told me that. I'd have brought my AFMU with me.
It'll be fine.
The classic Plater phrase.
Yeah, I'm never.
It'll be fine.
This
is fine.
I'm never not definitely maybe not sometimes not wrong. Anyone convinced by that?
Nope.
So okay, well that's a shame. But yeah, so neutron stars. We're going to talk about what Frontier have got right and also what they could improve upon. Not wrong. What they could improve upon. Neutron stars. Do you think they've got them right?
To some degree. The Jets is, I don't know if I would actually expect them to be slightly too small, to be honest. We often see these jets being visible at the scale of, well beyond the original solar system. So they should be quite a bit larger than they are right now. But I think the size, they got the size and the mass and the temperature. They got that pretty accurate as far as I know. Again, I have not been looking at that many neutron stars, but the one I've looked at has been reasonable, from my point of view at least. And I actually like, and I've never noticed that, they actually left, if you look directly at the neutron star, they actually left like a small cloud around it, which should be the remnants of the original star that it was formed from after the star died. Because basically a neutron star is when a star comes to the end of its life. That can happen several different things, and it mainly depends on the mass of the original star. So if we start with the very low mass stars when they die, they will essentially run out of hydrogen to burn in the core, and the star is being held up by, you have of course gas pressure pushing the star outwards, and you also have the radiation pressure that we talked about earlier also pushing the star outwards. So pressure from the light inside the star pushing it outwards in broad terms, and then you have the gravity trying to pull it in, and all those forces balance each other out. But as the star then comes to the end of its life and it runs out of hydrogen to burn, then the whole fusion process stops, removing the radiation pressure. So suddenly you are lacking pressure from the core, and this will causes the core to begin to collapse. So the core of the star will begin to collapse. If it's a small star, what happens is that the core collapses and the outer shell around the star, so what we would distinguish as the quote-unquote atmosphere of the star, and the outer layers of the star will then just be expelled outwards into a planetary nebula, and they can be pretty nice to look at. And what you would be left with would just be some brown dwarf somewhere, some pretty hot stellar core just sitting there, giving off all its heat into space and into this nebula. And this nebula will then eventually collapse into form a new star, and everything will start over again. But if the star is slightly larger, it can go through several phases where the core begins to collapse, and when it then collapses, it heats up and will then begin to burn helium instead of hydrogen, and then it will actually start the whole process over again, and then eventually run out of hydrogen, and then everything goes over and over. You can have this happen many times. But if the star is large enough, you will have this neutron-rich core left, and just as we talked about earlier with the figure skater, as it collapses, it will begin to spin faster and faster, which is why you see the neutron star spinning so quickly. And now I'm getting into a territory where I'm a bit in doubt, but I'm pretty sure I've heard of stars spinning a lot faster than this. We are talking about hertz, 40, 50 hertz maybe. I'm not completely sure about that, but I think we're looking at some stars that spin at that rate. So basically it should spin 50 times a second sometimes.
Wow.
Yeah, that's very quick. And again, that depends on that initial cloud that the whole star was formed from, how fast that was spinning, how fast the star be spinning, and how big the star is. A lot of factors that...
Now, quick question. What are neutron stars ejecting?
It's basically a plasma. And what a plasma is... So it's another state of matter. So, I mean, a gas and solid and liquid is pretty common, and people have a pretty good understanding of what is a gas, what's a liquid, and what's a solid. But there's not a lot of people who have an understanding of what is a plasma.
Yeah.
So if you let's take water, you freeze it, it becomes a solid. Then you heat it up, it becomes a liquid. And then you heat it up again, and it becomes a gas. But if you keep heating it up, it becomes a plasma. And the reason why we don't really see it is because we don't see any materials that naturally goes into this plasma state on the surface of our planet. But the whole star is actually, every star is actually a plasma. And what it is when you get into a gas, you basically have these atoms floating around freely. But as you heat them up, you will begin to knock the electrons off the nucleus of the atoms. And eventually you will get to a state where all the atoms in the gas have been stripped completely of its neutrons. And that's what you call a plasma. And it's quite fun because when they get into that state, because you have these positively charged nucleus, and you have the negatively charged electrons all floating freely between each other, whereas the atoms would in many cases be pretty close to neutral when the electrons were orbiting around them. Suddenly this plasma would actually be acting to magnetic fields, so it would be magnetic.
Okay.
And this gives all kinds of interesting effects. For instance, the northern and southern lights, or aurora borealis. That is actually caused by a solar wind or an outburst from the sun being caught in the magnetic field around the Earth, and then because they are magnetic, they will be running along the magnetic field lines and then entering the Earth's atmosphere at the top and at the north and southern pole, because that's where the magnetic fields are weakest. And as this plasma moves down through the atmosphere, this causes this northern and southern light.
Oh, sorry, I've just managed to drift into the ejection cone. I don't know how I've managed to do that. So I'm just going to grab my neutron boost whilst I'm here. So guys, please be nice. There we go. Got it. First time. It's good. So I was going to say, when people talk about kind of what plasma and not really having much of an idea of it. Now, technically, correct me if I'm wrong. I could be. Fire is plasma, isn't it?
I'm not completely sure, but
damn.
I'm actually not sure if it qualifies as a plasma. It could very well, but I'm not 100% sure.
I also thought that lightning was as well, like that what you see of lightning is technically plasma.
That's probably more likely, due to the extreme temperatures. Lightning is a lot hotter than the flame. I mean, the flame is what, a couple of 100 degrees, and I think a large bonfire can get up to what, a couple of 1,000 degrees at the core, which is, I mean, it's hot but I'm not sure if it's hot enough to form a proper plasma. You could probably, I mean, the funny thing about a plasma is it's not as the going from a gas to a plasma is not it's just like just stuff melting. I mean, either stuff is a solid or it's liquid, and you don't get anything in between. But you can do when you go from a gas to a plasma, because you can get to a state where the atoms have had some of the electrons stripped, or only some of the atoms will have their electron stripped. You can kind of have that middle ground. So it's hard to say when is something a plasma or when is something not a plasma. I mean, if you want to have it a completely degenerate gas where all the atoms have been stripped of their electrons, then sure, that's definitely defined as a plasma. But how big a percentage of the gas needs to have the electron stripped, and do they only have to have stripped half of the electrons before it counts as a plasma? It's kind of a fuzzy line. So that's why it's a difficult question to answer if fire is actually a plasma.
Okay.
It's closer, but is it close enough?
Gotcha.
One of the comments here in chat says that he's looking for a way to get college credits for watching and listening to all this.
Actually, Qualified has made quite a good point saying the sun isn't fire. And
the sun's not fire.
Yeah, like you wouldn't be able to extinguish it with water.
No.
You know that's
quite the
I
opposite.
think
it
that's
actually heat up.
I suppose it would then separate the water and use the oxygen and hydrogen and use it as fuel, essentially, wouldn't it?
Mm-hmm. Because, so as we talked about before, the fusion process only takes place in the core. So let's say that you took a rocket and you went up to the sun and you just poured tons and tons and tons of water, which would be absolutely nothing compared to the mass of the star. But let's imagine that you could pour a huge amount of mass onto the star in form of water. You would just increase the mass of the star, and what that would do is it would increase the core pressure in the star, heating up the core, making the fusion process run faster, heating up the star. So you would just be heating up, the star would just be hotter if you put water onto it.
Cool. Cool. That's what I've got as an answer. And Nathan's question. I wouldn't say huge stars.
So I've been through this cone 3 times now. It's a shame you can't just keep stacking it up, but I guess that would be a bit...
Well,
I would do that until I could jump across the galaxy.
Now, obviously, I don't know if you've seen the method where if you can charge your FSD at the right time, you can then re-enter the ejection cone.
Yeah, I know.
And then, yeah, I mean, I've done that a couple of times, but man, that's tough. That's tough to do, especially if it's a really fast-moving one, because you just get thrown out. Okay, I think. So let's head to the next target system. Give it a go anyway. See how far we can get.
Oh, you posted the destination somewhere?
I am just gonna bung it back in the Zencast chat. So that's the next one. Let's see how far away that is. Because I might be able to do. How far is it? 286 light years. That's definitely not being able to, it's not doable in one jump at all, is it?
Yeah, I can jump 221 with the current fuel I have.
What? This is madness. Well, it's 286, so it's going to be a little bit...
Oh, 86? No. So that's going to be 2 jumps for me. No, hold on. Yeah, 2 jumps should do it. 3 jumps maybe.
So yeah, I can go...
Did you post
200?
Oh, there we go.
Yeah, I can get 200 in there, so that's good. I thought this might be a great way for us to do. Proximity is going to take you a little bit longer, isn't it?
Yeah, a little bit. I got to figure out how I'm going to plot this too, because it doesn't want to. It doesn't want to plot route, because it's going to take more than. Ah, crap! Where the heck are we? All right.
Andy's just said that looks like the double neutron jump has gone. Aww.
They may have finally fixed it.
Well, I don't think it needed fixing. I think that was definitely a feature.
That was an unintended feature, I think.
Definitely not a bug. And they're talking about wormholes.
I don't think that wormholes are really a thing. At least I don't think so.
I think that theoretically they should, but they should be so unstable that they should collapse the instant they are created.
That's a little crazy to think about.
Yeah, because all I know is that you're able to get from one quadrant to another safely, but you've got to watch out for the wormhole aliens or the prophets.
Oh,
that's where the Thargoids live.
I was going full Star Trek DS9 there. So
yeah, and Voyager.
Yeah, Voyager as well. Only good for communication, but that's technically across time.
No, they had the Ferengi that they sent back all the way to the Alpha Quadrant with the wormhole.
Oh,
remember that episode?
Yeah. Ugh.
Fat Waffles ask, what's my thought on Dyson spheres? So maybe we should start by explaining what a Dyson sphere is.
Yeah, go for it.
It's not a vacuum.
Like a really advanced Roomba.
Kind of. A Dyson sphere. It's a theory that if an alien race at some point would have developed to a point where the total energy consumption for the whole race would be on the scale of the output of stars. So like one race would need enough energy that one star wouldn't be able to supply enough energy. One way that they could do that to actually harvest all the energy from the star would basically be to build like a big ball around the star and then basically coat the inside with solar panels, and then just have like a huge USB out plug on the outside. You would then go there and charge your spaceship or something. So the main problem that I see is, regardless of how you twist and turn this, these things were going to be so huge that they would require more mass than would probably be available if you demolished all the planets in the system. So you would actually have to demolish not only the planets in the system, but also the planets in the surrounding systems, and bring all that material to actually build something like that.
That's insane.
So, as interesting as a thought it is, I think it's highly unlikely. Should we head to the two black holes that are next to each other? I don't know how far away they are.
There's actually 3.
Yes. There are 2 of them that are orbiting each other.
Yes. This should be interesting.
Oh, it's only 600 light seconds out.
So yeah, funny enough qualified when you were talking about the idea of
USB 55.5 Type G.
when he was talking about can we go and talk about black holes, well, you get your wish.
Mm-hmm. The Dyson swarm is far more likely.
You see Balrog's comment there?
Yeah.
No, we're not going back to Beagle Point already, Balrog. Not yet.
Now, yeah, so with the Dyson sphere, this is something that, at least from a humanity point of view, wouldn't it be better for us to have essentially a Dyson disk that would essentially encompass the entire habitable zone?
A Dyson donut would probably be more feasible.
Oh yeah.
It's also very unpractical if you're actually gonna live in that system, that you need to have a hatch somewhere every time you need to go in and out of the solar system. Assuming that if you are capable of building something that scale, you probably have figured out space travel pretty well.
Yeah.
But who also made a comment about Dyson swarms, which is far more likely. Yes, I think it's far more likely scenario that you would have a swarm of small satellites with solar panels on them just orbiting around a star. That should make it a lot more feasible to do.
Oh, this is a pretty unusual system that we're in.
I'm not even there yet.
Oh, dude, it's an interesting system. I just said so.
You're killing me. You're killing me, Smalls.
But yeah, you've got two black holes that are orbiting each other.
I feel like there's a your mom joke in there somewhere.
Yeah, one of them's your mum. There you go. Is that right? And they're both orbiting your mum. How about that? Are we good? Are we good now? Is the obligatory mum joke? Yeah.
Oh, so Matt just posted a very very internal joke. He asked if nuclear birds are a possible race to live in the universe. And it's a reference to I've been playing Stellaris lately, and the race that I'm playing is basically ravens in space who just like to run around the galaxy, picking up stuff and collecting it for no apparent reason, just because they want it, because it's shiny, and then they have nuclear missiles.
Sounds good.
Yes.
Nuclear birds.
Nuclear birds. Yes.
All right. So is it like the next iteration of Angry Birds? Is that what that is?
Yeah, something like that. So I'm on my way inside a black hole right now.
I'm gonna try and fly in between them. Because what could possibly go wrong?
Everything.
Shh. For science.
Oh, of course, it puts me in a different instance to you guys.
I don't think it does.
No, I see. Oh, I see you now later.
Oh, I love the. It's always nice to be close to a black hole. It looks so pretty.
True, X.
It's like it should be more like, huh? Your mum. She must be a Sagittarius. Sagittarius A, judging by her mass. Come on. Come on.
That one's painful.
Ah, well, we like a good painful.
She must be a Sagittarius. Sagittarius A.
God.
Yeah. No. All right. Not my best. I'll give you that. This is actually not as cool looking as I was hoping, the flying in between two black holes, because you can barely tell that they're there.
That's the point of them.
What she
they
said?
Don't really emit much light. They do emit a little bit, though. There are the Hawking radiation, which sounds weird how something can actually escape a black hole, but apparently something can.
Yeah.
Okay, we can try to explain Hawking radiation. And a disclaimer: we're gonna go into quantum mechanics, and I'm crap at quantum mechanics.
Yeah, me too. Yeah.
Yeah, totally.
I almost failed that course. Both of them actually. Yeah, there are two courses when you study physics that basically half a year that's just dedicated to quantum mechanics. But I think the general idea about Hawking radiation is so in quantum mechanics everything is based on chance. You work with the assumption that nothing has an exact position and nothing has an exact speed. You don't know exactly how fast something is going or exactly where it is. So everything is like a distribution of probability. And everything stays in this distribution of probability until you measure it. So, which kind of seems weird that just by observing the world you change the state of it. But apparently that's how quantum mechanics works. And that's why it's not intuitive, and you just have to accept that quantum mechanics is weird. But the idea about Hawking radiation is, imagine that you have some atom very close to the event horizon. That could be a photon, very close to the event horizon of a black hole. Now, you don't know exactly where it is. There's a small chance that it's gonna be just outside, and there's a chance that it's gonna be just inside the event horizon. And then suddenly, somehow, and this is the part that I'm not really sure about, somehow the photon can suddenly just slip over the event horizon. So it's now just like a tiny distance outside the event horizon, but since it's traveling at the speed of light, it will actually have enough speed to escape the black hole. That is the theory, though, which is very weird, to be honest.
So, Proxim, do you want to re-explain that for us, just to make sure everyone understands?
No, because I don't understand it, really. I'm just over here trying to shoot the black hole from 27 kilometers away.
Yeah. See, now
That kind of
what I'm trying to do is get the black hole in between, my ship and the star that's there, to see what it would look like. And, it changes nothing. That's disappointing.
Really?
Yeah. It's going to be, that's technically a black hole eclipsing a star on my screen at the moment, and it just looks no different whatsoever. Like, there is literally no difference.
Okay, so it's warping the background stars.
Just not the one.
So now that we're talking about black holes and something frontiers should change, that's one for you right there.
Yeah.
Now, if you come right up onto the exclusion zone and you just start like spinning around in circles, the skybox does some really weird stuff.
I need to get my angle right so that we've got the star, because I want it to happen. It's got to look just right.
Yeah, I got it exactly at the center of the star. Nothing happens.
Oh man. Oh. Okay. Yeah, nothing happens. That is disappointing.
Very.
Yeah, and I've hit the body exclusion zone as well. Oh. Okay.
So that's okay. Just shoot the black hole. It'll be fine.
Got no weapons. I mean, I could launch a heatsink into it.
I got weapons.
So if we should try and explain exactly what a black hole is, so if you're standing on the surface of Earth, for instance, you have something called the escape velocity, and that is the velocity at which you need to go in order to completely escape the planet's gravitational pull. So this is the speed you need to go in order to get outside the planet's gravitational pull and never come back. And for the Earth, that's around 11 kilometers per second. So if you could stand on the Earth and you could kick a ball at 11 kilometers per second, apart from the fact that it would probably burn up in the atmosphere before it got anywhere near getting outside the atmosphere, it would potentially just disappear and never come back. It would never fall back to the planet. Now, and you can imagine the heavier and smaller an object is, the closer you are to the center of the object and the more dense it is, the higher this velocity is. And eventually, you would get an object that has such a high escape velocity that it exceeds the speed of light. That means that not even light can escape any longer, and that's when you get a black hole. So what we see as what people refer to as the event horizon or the Schwarzschild radius is essentially just the distance from whatever inside, where the escape velocity goes from being higher than the speed of light to being lower than the speed of light. So it's not actually the size of the object, and because we have no way of measuring what's actually inside that event horizon, we just have to assume that whatever's inside is just treated as a point mass. So it's basically just mass without any volume. Does that make sense?
Mass without volume.
Yeah, we just treat it like that. It's in reality, it's probably not, but it's the best approximation we have. That is just mass without volume.
I said that's an interesting thought, and I'm trying to wrap my brain around that, and it's not happening.
Yeah. I don't have much words for that, but I do, because I was about to go, yeah, but what shapes a black hole? I say something really stupid. I feel like
actually it's one of the only things in the universe that is a perfect sphere. Almost, actually. It wouldn't be perfect because that depends on the object. If we assume the object inside is a point mass, so if it's mass without volume, then the event horizon would be a perfect sphere.
Okay. Black holes.
That's one of the only things in the game. So one thing that would be that I would feel as odd, for instance, let's try that. What would actually, I mean, if we're sitting here, we're sitting, what, 27.8 kilometers from a black hole right now.
Yeah.
Assuming you guys are at the event horizon as well. Now, you could argue that if we were to go any closer, we wouldn't be able to get away because we would potentially get inside the event horizon. But our ships is capable of traveling faster than the speed of light. So technically that should allow us to move away from the black hole. But if you did a reboot of your ship, what should happen, because I mean now that we are not in super cruise, we should be pulled in and we should be dead by now. But clearly we're not.
No. I imagine that would kind of, I feel like it would suck a little bit if you were to, oh my goodness. When you guys see this on stream, it's going to look super weird. But yeah, like, that would make for a really boring game, wouldn't it? Like,
no, I think it would be quite fun.
Kind of the oh, I've died. Oh, I've died. Oh, I've died. Like that kind of thing.
I mean, if you're gonna, if your lead is supposed to be a space sim, and if you go, ooh, look at that black hole, I wonder what happens if I go too close. Well, what do you think's gonna happen? You just made the black hole slightly larger, or slightly heavier.
Yeah, I suppose there would be that. So, what happens if additional mass is added to a black hole? Do we know that? Like, would it just continue to
grow? Yeah.
And do black holes then become something else or not?
They just become bigger.
Like, does their energy get dissipated?
That's back to the quantum mechanic and Hawking radiation thing. So technically, yes, there are some, but it's very, very little. But one of my cosmology professors, she described a black hole as a baby. It just sits there on its ass and it eats everything that it can reach. And once there's no more mass in reach, it just sits there doing nothing. That's basically how a black hole works.
Just like a baby.
Yeah.
Okay.
That was her explanation of what a black hole is, how it works.
And I just want to make sure it wouldn't be simple. Like, if you were talking about what's that space film called? That space film that's like Interstellar. Wow, that was tough. Mm-hmm. Interstellar. The whole getting away from the black hole by just turfing out your robot. Spoiler alert. Oh god. That wouldn't help you, would it? Lightening your load, surely, because you're still like
no. The only thing that really matters is how fast you're going. I mean, you could argue that if you push the robot into the black hole, that would give you a little bit of a push outwards. But that would be on the scale of a spaceship. That would be next to nothing. If any of you guys know of a webcomic called XKCD, It's absolutely wonderful. They are very nerdy, so just warning. But they are absolutely wonderful. And he has a blog where he takes in questions and then spends too much time answering silly questions. And one of the questions he got was, would it be feasible to have a spaceship only powered by a man with a huge amount of golf balls? So basically you have a man standing at the back of the spaceship hitting golf balls away, and then you would get a kick every time he hit the golf ball. Just like if you have two people on office chairs and you put your legs on the other person's chair and you push away, you will both get a push in opposite directions. Same thing would happen with the man on the golf balls. When he hit the golf ball would get a kick away from the spaceship, and the spaceship would then get a kick in the opposite direction. And that's basically the same thing that would happen with the robot you talked about before. If you push the robot into the black hole, you would get a small push outwards. But in terms of mass, it wouldn't really matter.
Okay.
So I guess that was just done for the emotional effect of losing the robot.
Gotcha. Pineco, it's science. It's okay. Not biology. Physics.
Biology and science, kind of.
Yeah, but apparently not a great one, because there's also squishy things. If you're Sheldon, that's what you say. But yeah, I just want to point out that like how odd this system is, and this is bubble territory as well. So the system that we're in is HIP 63835, and it is rammed full of different types of stars of varying different sizes, 3 black holes, and a few gas giants. So if anyone does fancy checking this place out, mark it down, and you are more than welcome to obviously have a look at it. There'll be no first discoveries though, but you have to drop that in chat, which I think this is probably the most interesting system I have seen.
And I would imagine the system being very young, most likely. At least if you look at the star. How old is the main star actually?
Main star, 502 million years.
Yeah, so that was basically created yesterday. I mean, our star is what, 4.5 billion years, something like that, ish.
Something like that. But then the interesting thing about this is it has the black holes at the same age.
That would probably be what? They're the same age.
Yep, they're all 502 million years.
That's weird.
Oh, look at that.
Everything in this system's 502 million years. I'm just checking them all one by one.
Mm-hmm. I think we're on that thing that we would rather they improved on. Possibly this.
But you can always guess at the age of at the age of a star, because if you see a very blue star, a good guess would be it would be very young. I would say if it's over a billion years old, it's probably very close to going supernova. If it's that size, and if you see a very red star, there's a good chance that it's going to be very old. Not because stars get redder when they're old, just because red stars lives longer. In astrophysics, we often call the big blue stars for the rock stars, because they live a violent life and die young.
Yeah, I would say that makes sense. Now, the brown dwarfs.
Yeah.
So they're kind of like gas giants that didn't quite make it to stars, basically, if you were to give them a very basic explanation, right?
I
knew you were going to do that. Or say kinda. It was going to be one.
So it can both. So brown dwarfs, yeah, it would be the stars that didn't quite get hot enough. They didn't have enough mass to get that initial fusion process started in the star. So basically, the initial cloud of gas that was formed from was too small to form a proper star. Not that they are not proper, but like, you know what I mean. Just like Pluto's not a planet.
Pluto's a planet.
It's a dwarf planet.
Leave that poor guy alone.
It's a dwarf planet. I thought that dwarves are planets too.
I've actually seen some place where they refer to what is commonly known as dwarf planets as Plutoids, just because people think it's they have pity on Pluto for not being a planet, so they call it Plutoids.
It's planetism, discrimination.
Planetism. That's not a thing.
It is now.
No.
Yes.
No.
Everyone in chat, help me defend planets from discrimination. Pluto is a planet. We must defend it.
Have you been drinking in preparation for your bonus stream yet? Okay, good.
Not yet.
Just making sure.
We got a little bit yet.
Matt says brown dwarfs is just stars that were accepted into the star gang. So sad.
And actually, the whole question on like, do black holes rotate?
Yes, they do.
They do.
We
okay.
assume they do. Again, that's so. There's no reason to assume that they don't. But we distinguish between two types of black holes, and we actually only have one of them in this game. And these are what's called passive black holes or non-active black holes. But you also have what's called active black holes, and East Engineer posted in chat saying that it's a shame that they don't have accretion disks, because again, everything in apparently the universe likes disks. So when you have a black hole, and it's still pooling in mass, that with the whole baby thing earlier, if there's still mass within range that it can eat, it will be in a disk and it will fall onto the star, onto the black hole, and that's what we call an active black hole. And when we see these disks, we would assume that they would be rotating because of the black hole. So we would assume that they are actually spinning. But you should not think of a black hole as a hard physical object. It's just the outer edge is just some odd line in space where the escape velocity goes over the speed of light. If you imagine that you could go closer to the black hole, go to the event horizon without being pulled in, you would not be able to put your hand on. That's why it's an event horizon. It's not an event surface, because it's not a physical surface. It's just some distance in space where the escape velocity goes over the speed of light.
Okay. Black holes are not physical objects. Got it. That is what I picked up on what you said.
There are probably some physical object inside that horizon, but we have no idea of determining the size of that, the rotation speed of it, anything. Temperature, nothing. So that's why we assume it's a singularity or point mass.
Okay.
Oh, black holes, sci-fi nonsense. Got it.
Yeah, that. I don't know if either of you two have seen the film from the 80s, The Black Hole.
Nope.
You know, you've never seen any of the films, Proxim.
I have two. Just not the same ones that you have.
Yeah. Now, Astro, he hasn't seen Aliens. What's your opinion on that?
Let's not start this again.
How can you be playing space games and not seen Alien?
That's exactly what I say. I'm gonna keep doing this until you watch it, and you have literally no excuse. Like,
I do too.
You can just pop a film on whenever you like. You're not streaming, pop a film on. That's it. Just do it. Just do it.
Yeah. See, Waffles. Thank you. Someone else that's never watched it. Thank you.
Now, Waffles, I'm gonna assume you're not the same age as Proxim. I'm gonna imagine you're probably a bit younger than him, and that is a bit of a guess. So do correct me if I'm wrong, but he has no excuse because, at least with Aliens, it's kind of a military-esque film. It's not like a psychological alien horror. It is a sci-fi war film, basically, with aliens. And it's, yeah. He should have seen it. Now,
I'm just going to sit here and silently shake my head at you.
If it wasn't because of copyright, you should do a Proxim Watch Aliens live stream.
Yeah, that'd be a reaction stream that would be worth seeing.
You know, I might do that on Rabbit, but not YouTube.
I think YouTube, your stream wouldn't last for long.
Technically, you could do it without sound, so that you could hear it, but the audience couldn't, and you could just play classical music over the top of it, and that would be a hilarious stream.
Be an ironic stream that people would watch for about 30 seconds and go, "What is this nonsense?" and then leave.
Well, yeah, just watching you react. If they could hear you react to it as well, that'd be good.
I could make that happen.
Now,
actually, and pretty soon they'll be able to watch me react. Actually, now that
oh yeah, that's a good point.
Yeah.
I mean,
that's
wow.
the thing now, guys.
And people chose that. Wow.
I know.
Yeah, and Proxim's getting a webcam for his streams.
Nice.
I actually have to rearrange my room so I can make this work properly too.
Yeah, he's got to move the inflatable doll around. So,
And all the sex toys, take that down from the wall.
yeah, probably put away the chains.
Yeah. None of that. None of that.
Dry the gimp suit somewhere else.
Yeah, that's got to go in the closet.
Yeah. I was going to suggest we go over to V886 Centauri, which is obviously one of my favourite systems to bounty hunt in, but I thought we'd go there because it's got a white dwarf.
Okay.
And we'll
Don't make fun of my height.
Look at them. Oh.
You had to have known that was coming. Come on.
Yeah. Oh yeah, that's a good question. Do you... Time. I'm going to say time. Do you know why time is affected by gravity? I mean, no one knows why, but could you talk about it a little bit if possible?
Affected by gravity. So, okay, so if we should get into the whole relativity thing. What breaks everything is the fact that the speed of light is constant. So, imagine that I'm sitting still somewhere in space. I've dropped out of Super Cruise and I'm just sitting still, and I'm turned on my headlights, and I would then measure the speed that my headlights would be moving away from my ship. I would see them move away at the speed of light. Obviously, that should be pretty obvious.
Yeah.
So you're flying by in Super Cruise, and you're flying half a C, let's say half the speed of light. And you have your headlights on as well. What speed would my headlight be compared to you? Well, the obvious answer is, well, since it's moving 1 C away from me and you're moving past me at half a C, you would see them move away from you at half a C.
Yeah.
But they don't. They move away at 1 C. The same does your headlights. They also move away from you at 1 C. It's always constant. The speed of light is always constant.
But that doesn't make sense.
No. But for that to be true, something else have to give. And that is time. So the faster you go, you need to get this right. So the faster you go, the slower time will progress. And that's very weird. But
so the secret to living forever is to go really fast.
But that
that's actually something called the twin paradox. Oh, did you post a system that I need to go to? I'm just flying around looking at black holes.
Oh no, I completely forgot to do that.
There's actually something called the twin paradox, that you imagine you have two twins living on Earth, and one of them stays on Earth, and the other one would fly away from Earth in a rocket, and he would then fly somewhere close to the speed of light, and then at some point he would turn around and come back. Then, when he comes back, the twin that stayed back on Earth would be older than the twin that went away on the rocket. So from the guy on the rocket, from his point of view, he would have traveled forward in time.
Now, didn't NASA do this? They said they had twin astronauts, and they sent one to the International Space Station, and they kept one on Earth. And they worked out that over the course of however long it was, one of them was like, I don't know, 8 days older than the other or something.
Oh no, I think we're talking microseconds.
Oh, okay. I knew it was a small amount, but I thought it was 8 something.
It's very small amount, but it's enough that, for instance, GPS satellites, they move at not nowhere near close to the speed of light, but at a significant speed compared to the speed that we move when we walk around down here on Earth. And the way GPS satellites work are that you basically send a timestamp to the or you ask the satellite for what time is it, and it will then send you the time, and then you get the timestamp from all these different satellites, and then you compare them, and based on that you can tell how far the different satellites are apart. But because they're moving so fast compared to you, and because you need to get those timestamps very, very exact, you need to compensate for the fact that time for the satellites moves slower than for you. So the clocks on these satellites, GPS satellites, are actually adjusted for the relativistic effect that they're moving fast. Otherwise, the GPS system will slowly drift away, so you would get larger and larger inaccuracies in your position as time went on. You constantly have to recalibrate.
Isn't it something like a full second a month? Is it a month or is it every day? Can't remember.
I don't think it's something like that much. I think we're talking very small amounts. Oh crap! You're kidding me. Please let this star be scoopable.
Better make a rookie mistake.
Yeah, I was too busy. Okay, this looks very scoopable. I was like, why am I not jumping? Yes, this star is scoopable. I'll be there again. Enjoy scooping fuel in the Diamondback.
That's fun. That's my only problem with the Diamondback, is the fuel scoop size.
It's very good for getting around the bubble, because you can normally get there with the fuel you have from one station to the next, or you will have to fuel through very little along the way.
Okay, now I have just arrived at V886 Centauri.
I am
beautiful white
jumps
dwarf.
out. White dwarf, yeah.
White dwarf.
Okay, so white dwarfs are. We need to go back to the life of stars, and we haven't actually gone through the whole life cycle properly yet. So I think that would be a good point to do that right now.
Yeah, sure.
I think I have enough fuel to reach the system now. I hope. Otherwise, there should be a star in the system that I can scoop on. So, we already talked about how the whole gas cloud collapses and planets are formed and the star moves into its main sequence. We have everything that's collapsed, and the star is now moved into what's known as the main sequence. And this is pretty much almost all the stars that we see are somewhere in the main sequence. And this is where they will spend the majority of their life. And then depending on the mass of the star, different thing happens when it dies. And as we talked about, the stars at the end of their life, they run out of hydrogen in the core. So there's no more fuel, basically. It runs out of fuel. And A funny thing about that is, if you... So we talked about that the star or the sun is a plasma, and you have these positively charged nucleus that bump together, forming larger atoms. That's how the stars is actually forming heavier and heavier atoms, by smashing two small atoms together to form a large atom. But they both have the same charge, electronic charge, or electric charge. So it's basically like taking two magnets with the same pole pointing towards each other and try to bump together. They will try to repel each other. I guess we all tried that at some point, try to take two magnets and put them together.
Yeah.
Did one way they would attract, and the other way would repel each other. So that depends on the temperature of the core, because the hotter it is, the faster these nucleus are moving. And if they're moving fast enough, they should bump together, get close enough that they will fuse together in this fusion process and form heavier elements. So they will make hydrogen to helium. But the temperature in the core of the sun is nowhere near hot enough for that process to happen at all. It's way too cold. Which leads us back to the whole quantum mechanic thing, that they sometimes do a thing called tunneling. So they're moving towards each other very, very quickly, but they do not have enough speed to actually hit each other. But then suddenly they snap, and then they're suddenly very close to each other, and then they actually hit each other. Because quantum mechanics is weird. But that takes place, and it converts hydrogen to helium. And at some point you run out of hydrogen. And of course helium has two protons in the core, making it have a slightly higher charge, like twice the charge. So it's more difficult for the nucleus to hit each other, so it needs a higher temperature. So what happens is, when it runs out of the hydrogen, the core begins to collapse and heats up. So the core of the star begins to contract and it heats up. If the star is small, it would just expel the outer layers, as we talked about, and what you're left with is a white dwarf, which is basically the hot core of a star that's left sitting there in space, just blasting out its remaining heat. But if the star is hot enough, what will happen is, as the core contracts and heats up again, it will then begin to reach a point where it can begin a helium burning phase, and it will then burn helium into carbon. And then you would around that core, you would have like a shell, where the temperature would now be hot enough for hydrogen burning to start again, because you've only used all the hydrogen in the core, but you've not used the one in the atmosphere around it. And that process can go over many, many times. Then you would go from burning carbon into heavy and heavy elements until you hit iron, basically. And you would get all these layers, just like an onion. You would have different shells outside each other, burning lighter and lighter elements the further you get out. And then eventually either the star will go into a white dwarf, or they will explode and become a black hole or a neutron star. Neutron star is just the next step up from a white dwarf. Then it's like white dwarf, neutron star, black hole, depending on the size of the star when you start it.
Okay. Wow.
So this is basically the remnants of a dead star.
And how long would a white dwarf stay as a white dwarf for-ish?
It can do that for a long time.
I mean, obviously talking billions of years.
Because the rate that it's dissipating heat, the light is basically just... I mean, some of the energy is dissipated through light, of course. But the rate that you're dissipating heat is actually very slow. And all that scenes that you see in sci-fi movies, where you would go into space and you would instantly be flash freezed. That's not how it works at all. So the average density in the universe is something like 4 atoms per cubic meter. That's not a lot. That's very, very little.
Yeah.
And what heat transfer is, as we talked about earlier, heat is essentially just the atoms moving faster. So what you feel as heat is basically the fast-moving atoms, either in a gas or if it's in a surface that are hitting your hand or whatever that is you're touching it with, and dissipating some of that energy into your skin, and that's what you feel as heat. So it's nothing but kinetic motion. I mean, this is again roughly, but it's basically just kinetic motion being transferred from one object to another, or from one gas to something else. But if you're in space and there are basically no atoms around you, there is nothing to transfer the heat away from you. So even though the universe have an average temperature of 4 Kelvin, it would take a long time for the heat to be dissipated away from your body, because there's nothing to dissipate away to.
Now, see, I had this discussion with my friend who is a aerospace engineer, and we regularly have conversations about physics and stuff. And I said to him, I went, so hang on, wait, in space, how do you, because normally you lose, well, heat is transferred by CCR, so conduction, convection and radiation. And obviously you can't have conduction or convection in a vacuum, but you can have radiation. But it's IR radiation, isn't it?
Yes.
Yes,
that
I scienced.
Black body radiation.
I scienced.
What would actually happen to you would be pretty unpleasant. The first thing you would notice is everything would be very, very dry. Your mouth would dry up because everything that has liquid on it, so your eyes, for instance, or your mouth, all that liquid would begin to boil. It wouldn't be hot; it would just boil and vaporize. So your eyes would be very dry. Your mouth would go completely dry as well. And then, of course, there's the whole, your body would swell up, and it would pull out any gases that would be inside you pretty quickly. So lungs would probably be emptied pretty quickly, which I guess is not very pleasant either.
No.
So you would most likely die from being suffocated.
Approximately, are you laughing at what Black Skull just said?
Yes.
Yeah, well played to science. Shame it happened later in the stream. It's like, well, hey, got to science at some point. I'm not the science expert on this one. But yeah, so I understand as well, like, essentially your blood would boil, wouldn't it, in your veins, and obviously there'd be the rapid expansion of the gases.
No, because
is that...
your veins are still trying to keep the pressure in. Just as you can have a higher, if you go to this, if you blow up a balloon, there would be a higher pressure at the center of the balloon that there would be on the outside.
Okay.
Slightly, but it would. Yeah, and the same thing happens with your blood veins, blood vessels. They would try to keep everything together and keep it at a slightly higher pressure. So your blood wouldn't boil right away. It would only be the directly exposed surfaces that has some kind of liquid on it.
Okay, that makes sense. Which is actually the whole surface of your lungs as well.
Yeah.
That's really unpleasant. But it's...
I'm pretty sure it wouldn't be very pleasant at all.
No, yeah, from what I imagine, it definitely wouldn't be. Just after saying what we were talking about, yeah, that'd be horrid. Cool. I'm glad we established that being out in the vacuum of space would be really unpleasant.
In case someone was in doubt of that.
Yeah, yeah. In case someone was wondering why we don't just live in a vacuum, this is why.
Yeah, that's why. Space is death. Avoid space.
And of course, as we know, no one can hear you scream.
No.
As well.
Dun dun dun. dun.
That's a tagline from Alien, Proxim. Just in case you didn't.
I know.
Okay, all right. Just
that I know. I've heard that one so many times.
See
I'm
now
not gonna live
qualified.
this down, am I?
See now.
Christ, you've been on about this for months. It's been like 6 months, and you're still aliens. Aliens.
I've been on this.
Alien.
It's a really good series of films. You should watch it. And also, I've been on you about it since the very first Zencast.
Yeah, 6 months ago. I remember.
You need to sort yourself out, mate. That's
If there's no one to hear you scream, are you even screaming?
That is deep. That's like, whoa. That's interesting. I mean, I guess you are.
That's the same question as, does a bear shit in the woods? If you can't see the bear, is it still shitting in the woods? Same thing.
I'm pretty sure that's not the question.
Yes, it is. Because you can still scream. Being able to hear it does not necessarily mean that it is or is not happening.
I mean, yeah, okay. Let's call it Schrodinger's bear shit. Nice. The bear is both shitting and not shitting in the woods at the same time until you check, and then you know for certain. Nailed it.
One thing though that I would love to see them implement into the game would be redshifting when you travel faster than light. So basically, when you move quickly towards an object, you would expect the light to be blue shifted, so everything would look blue. Or if you moved away from an object, you would see the object being more red. Because lights are basically just waves. So you can imagine I guess most people have the idea that lights are waves, and the longer wavelengths, they are red light, and the short wavelengths are blue light. So if you're moving away from an object, you would kind of stretch light up that you would receive, and that would make it look more red. But we don't see that when we travel around, even though we're traveling many times the speed of light. But I guess one problem with it is that means as soon as we go over the speed of light, we wouldn't be able to see anything at all. It would just be black in front of us, I guess.
I guess that almost comes down to the speed of light thing, as the whole, if you're oh man, I'm struggling. I must admit, this is a lot of hard work.
And then ESA just brought up the whole Schrodinger's cat.
Is it both? Oh god, yeah. Is the cat dead, alive, or both, or is it shifting through time in both dimensions? What? Well, if you go the speed of light, you would be massless. I thought that would be. Isn't that the opposite? Like the faster you go, the higher your mass is. The closer you approach the speed of light, you have infinite mass or something.
Yeah. Okay. So it's the faster you go, it requires more energy to accelerate you, which equivalent is the same as your mass would basically increase. So you could. Problem is, if you have mass, you would never be able to accelerate to the speed of light. Only things that doesn't have mass can travel at the speed of light.
Right, so photons don't have mass.
No, they're massless.
But they can have the effect as if they do have mass on objects.
They have impulse. That's not the same as having mass.
Impulse. Oh god, it's another word. Okay. It's like, uh-oh. So, impulse.
Words are hard.
Words are hard, especially this many used in ways that I'm not used to. So, when we say impulse, what does that mean?
It's
in like the context of our conversation currently.
Impulse is just that's hard to explain actually. It's basically just it's not really direct. It's not really energy. Is impulse measured? No, impulse is not measured in energy. And it's the ability to hit something and disperse and give it some kind of energy in form of push. It's a little difficult to explain. I think it's.
Is that a way of saying that you can't explain it?
No, I can't really explain exactly what impulse is actually.
That is perfectly acceptable, because you could have literally said anything, and I would have gone, "Oh, okay," because I wouldn't know any different. Turgeon's gone deep. But all of that means that photons are coexistent with time. Every photon hasn't aged a second since the beginning of the universe.
True.
What?
Assuming the photon has lived since the creation of the universe, which is highly unlikely.
I'm sorry,
Oh,
what?
fuck. That's close. Okay, so that's going back to the twin paradox, you know, with the twin on Earth and the twin in the rocket flying away, and the one flying quickly is getting older slower than the one on Earth. So if the twin on the rocket is flying close to the speed of light, like very, very close, as close as you could possibly get, compared to the twin on Earth, he wouldn't age. His time would be standing still between the two, or for the twin in the rocket. He wouldn't feel it, but for the twin on Earth, he would see the time standing still from him because he's traveling at the speed of light. So that's why photons don't age.
Right. Man, that's Turgeon going in hard with the science there on that one. Well played, sir. Well played. So, hang on. So here's a point. Okay, right. So actually, funny enough, Akatu's comment there just gave me an idea. Is if we're talking about obviously photons never aging, now my computer screen in front of me, does that give off photons because it's light?
Yes.
Okay.
Everything that's light, heat, when you turn on your TV, that's all just photons.
Okay. And photons, if they don't age, do they get absorbed? They get absorbed, don't they? That happens?
Yeah, they can be absorbed. They can hit stuff and be absorbed.
Okay. Because I'm kind of thinking, does that mean the universe is constantly getting lighter and lighter?
No, because they do get absorbed.
Okay. So I suppose every time you see something...
But the universe is also getting bigger and bigger, so there would be more and more room for the photons to be in.
Okay.
Because the universe is expanding at the speed of light, at least for us. It's actually probably expanding faster than that, but we can't see it. So if we really want to go into stuff that's fucked up, then we should talk about galaxies moving faster than the speed of light.
Yes, nailed it. That's it. Coming towards the end of the Zencast, it's like, let's move on to some fucked up science. Bring it. What do we got? Go for it. Let's really mind blow everyone.
Okay, so when we look into the universe and we look at galaxies, what we see is the closer the galaxy, or the further away the galaxy is, the faster they're moving away from us. Okay? And that's because the universe is expanding. So it's kind of like imagine two ants on a rubber band. You might have the two ants walking towards each other, but if you're pulling the rubber band, they will still move away from each other. Okay, that makes sense?
Yep.
The distance between the ants would be bigger because you're pulling the rubber band. And the speed that the ant is walking along the rubber band, that's called its peculiar motion. That's the motion in space. But the velocity that the ants are moving away from each other is different from the speed that they're actually walking. So you can imagine that on a large scale with galaxies. So you could have a galaxy that moves through space at a speed lower than the speed of light. Let's say we have two galaxies that move towards each other at some velocity. But because the distance between them are so big and the universe is expanding, you could actually have those two galaxies moving away from each other faster than the speed of light.
Okay.
Not because they're traveling faster than the speed of light, but because space between them are expanding.
So, in this example, I'm imagining essentially the universe, and that's in inverted commas, to be a bit like a large sheet of elastic material, and you're talking about, so it's being stretched from all sides at the same time, kind of.
Yeah.
Okay. Yeah.
Kind of. Yeah.
So everything we see is getting older, but not as fast as we age. Wait, what? Did you say anything about that?
So everything we see is getting older, but not as fast as we age. I guess it's because everything is moving away from us so quickly.
Ah, yes, that does make sense now. Yeah.
And then the whole point of the further away we look, the older. I mean, the further back in time we also look, because it's taken light for so long to get down to us. So when we look at a galaxy far, far away,
we're looking at a galaxy a long time ago.
We look at how the galaxy was a long time ago. So if that galaxy is, let's say, it's 1,000 light years away. Okay, that's actually no, we wouldn't, because that's inside our own galaxy. Let's say we look at a galaxy a trillion light years away, something big. And that's actually too big as well, because that's older than the age of the universe. 1 million light years. That's probably a bit more feasible. So let's say we're looking at a galaxy 1 million light years away. We would see the galaxy as it was 1 million years ago, not how it is today, because it's taking the light 1 million years to reach us.
Yeah.
So that poor photon, or the photons, that's been traveling for 1 million years through empty space, avoiding everything, not hitting anything, just hits our detector and becomes a small electric signal. I kind of feel sad when I think about that. I think it's...
When you think about your place in the universe, that's when I think things get a bit weird, because you kind of have that... We are such a very small thing on a very small planet in a very big space, and we can't change any of it.
Nope.
Wow, if I've just made everyone feel like their lives are totally worthless, I am really sorry. That was not my intention at all. But just so you know, I've totally crushed my own world at the same time. But yeah, what I was going to actually... Oh, I had a really good question, and it went. Damn. Because it's going to be a good one. It's going to be like one that, well, I would like to know the answer to, and having a think about it. But no, it's gone. Black Skull, now I thought that was before you said it. Cool. I'm glad I didn't make things worse. Now, there were a couple of things that you wanted to... Oh, no, I've got my question back. I know exactly what it was. Right. Now, example. So, we're both sitting here in essentially the same type of ship with the same clock on screen telling us the same time. Now, if you and I were to go separate ways and jump around for a bit, you know, a few thousand light years, and come back. Now, surely, depending on the number of jumps that we've done, we would have different times on our clocks, or we should do.
Yes, we should. If I stayed here and you decide to jump to the next system and come back, it should have been on my end, it should have taken you years. On your end, maybe only 5 minutes. But that's very hard to implement in a game.
Yeah. Because that would be a bit like I were to leave the system, and then it would have to take me 5 years to come back, or you would have to.
In game, it would only have lasted 5 minutes on your clock.
Weird. That would be impossible to put in. But I thought that was worth bringing up and mentioning, because that would be a thought of us all having the same clock on screen. A little bit like if you're talking about in Star Trek, they have star dates. Surely, if you're travelling at the speed of warp long enough, you're not going to be working on the same star date unless every time you drop out of warp, you update it so that you know where you're up to. Kind of like right, this is actually where we are now. You have to constantly work out and calculate for the time dilation.
Yeah, and the fact that they at many points they would call back to Earth while in the middle of warp, breaking every laws of physics by doing that. Just the fact that they could have a conversation while being so far away breaks every laws of physics. There's no way you can send information that fast through space. It's just not gonna happen. Not with the technology we have today, at least. I mean, just imagine. I mean, in the hopefully not too distant future, when we begin to have people on Mars. Depending on where Mars and Earth is in relation to each other, it could take a radio signal 20 minutes to move between the two planets. So if you were having a Skype call with someone on Mars, you would basically say hello, and it would be at least 40 minutes before you would get a reply, because 20 minutes for the signal to reach the other end, and then 20 minutes back.
Yeah.
So imagine that ping.
Oh.
So if you're planning to going to Mars and play computer games, don't play anything online, because your ping is gonna be pretty bad.
Unless you've got your own Martian servers, and
yes,
then you'd be okay. It's like, yeah, I'm just logging into the Mars server. Awesome. I'd be right.
Yeah, I guess if they already have servers, depending on which part of the world you're in, I guess it makes sense that if you really want to go to Mars, you would have a server there. But that's probably not the first priority, to move a gaming server to Mars.
Yeah, see, I feel like that would be a real part of my life that I would miss if I were to move to Mars. Like, what would be totally cool being a pioneer and setting up on a new planet computer games, though.
Yeah, only solo play.
Oh, no. Like,
you can't even play Elite in solo.
You'd be responsible for completely your own BGS. I know. Like, there's super special server. No, can't handle it. That'd be awful. That would be absolutely awful.
Have you ever thought of that currently Mars is the only planet that we know of that is only inhabited by robots?
Yeah, that's terrifying.
Just let that sink in for a minute.
I, for one, welcome our robot overlords of Mars.
Yes.
Now, I'm going to have a quick look at the list of things that we spoke about to make sure we've got everything kind of covered off. So spoken about stars quite in depth, I would say. Planets, you did mention about the planet side of things.
Yeah, we've been around planets and looking at it. We've talked briefly on faster than light travel and the whole problem with time dilation and redshifting and not redshifting. And we've been around black holes as well.
Yeah.
And Matt says, "Oh, now I'm not going to sleep tonight." Great.
Fear the robots. Fear them. Oh no, sorry. Proxim, you can't be doing that. You can't be doing the firing in a pattern, especially of all patterns, that one, because it's just the most.
What?
Everyone honks their horn at like that here in the UK, and it drives me insane. Yeah, that one's pretty bad too. So I think we're going to call it time for the stream for this evening, because we've been going for just over 2 hours now, and that's what we normally go for. And so yeah, I just want to say, Astro, thank you very much for joining us. Everyone who is in chat, make sure that you go and check out his channel. The link is in the description of the stream.
Nice.
Go subscribe. Great content. Also has some quite entertaining streams as well, involving combat in small ships, and you've got one tomorrow, haven't you?
Yes, tomorrow we're bringing out the Sidewinders, and we're gonna go full mayhem in a hashless resource extraction site and just killing everything in Sidewinders.
Should be interesting.
We tried Eagles, it worked. Now we're gonna try Sidewinders.
Okay, Sidewinder combat, nice. As usual, again, I'm just going to have a quick reminder for everyone to make sure that you also subscribe to me if you haven't already. I'm seeing a lot of familiar people in there, so I think you probably already subscribed, and also to Proxim as well. Proxim is currently streaming a lot at the moment, and he's about to go on and do a drunken stream, I believe. Is that right?
Yeah. Goals for the week got hit, so we're about to do Player Unknown's Battlegrounds. I've not played it before, and so I'm going to try and learn it while hammered. So, yeah, that's going to be interesting.
Yeah, I don't know if it's the best time to do it.
I'm probably going to start it here in about an hour or so, roughly. So, yeah, that'll be a thing. My channel, it should be in the stream description if you guys aren't already subscribed to me.
Yeah, it definitely is in there. So, awesome. Right, so I will call it time there. So, I say it's goodbye from me.
And I will see you all later.
Yep. Goodbye.
Okay, take care, guys. Bye.